let's work with an example, a really basic example, and see where we go from there. Okay, suppose you have a line, and suppose you have a particle on that line, right? And this particle behaves with a Lagrangian x dot, which we know is velocity, right? So it's in terms of its position and its velocity. Those are kind of its free coordinates, if you like, or its general coordinates. We can then say that its momentum, this is something that we should know from basic Newtonian mechanics and so on and so forth, its momentum is dl over dx dot, right? And we can also say that the force is dl over dx. Now we can apply the equations of motion, the Euler-Lagrange equations, and if I'll just remind you of what those are, you've got d over dt, dl over dx dot is equal to dl over dx. Pretty simple, right? Let's have a look at dl over dx dot. We've already called momentum, and dl over dx we've already called force. So this is essentially d over dt. The momentum is equal to d over dt. In this case, if we d over dt the p, if we d over dt the momentum, then we're differentiating it with respect to time, which here I'm denoting as a dot. So we get p dot out of this part here is equal to, as I said, dl over dx is equal to the force. Brilliant. So that's literally just how Lagrangians work, and we get this beautiful little tiny relationship for this particle. The force is equal to the momentum with respect to time, differential of the momentum with respect to time. Now let's have a look at what symmetry would do to this. So in general, a symmetry just means that if we apply a certain parameter change, and I'll become more specific about what parameter change is. If we apply a parameter change to this particle, to the coordinates of this particle, then a symmetry implies that the particle's the position of the particle wouldn't change if we apply the parameter change to the position, which in this case would be meaningful, of course. I've got one way of representing this, which is quite easy to see, right? Imagine xy graph, and I draw you a parabola on this. Notice, I mean, I know this is really badly drawn, but notice, oh gosh, okay, you get the idea of what I'm trying to draw. Notice that for any minus values of x, you get the same result for y, right? It doesn't matter if you take plus 2 or minus 2, because this is an x squared plot. Minus 2 is 4, and plus 2 is equal to 4, right? And that's just one basic type of symmetry. So, in this case, we can we're going to apply just a bit more of a formal symmetry that is just basically a translation. And the translation goes as follows. Very basic translation, no worries. Your translation will go as follows. We take x and we send it to a new value of x, which is a function of a new variable constant, which is called s, right? So all the x values, and we send them to this new x, to a new x value, which is a function of s. Cool. If we do that, if we do it in this case, right, we make it related in terms of a function, a new function to the old, then we can do the following. We can say that d over ds of the Lagrangian with respect to this new x that we've created here, that we're sending these values to, and of course a new x dot. Alright, because just notice all we've done, we've just changed the original Lagrangian. We've translated it by what we said we'll translate it by. Right, we've taken x, we've changed it to xs, and by definition we'll take x dot and we'll change it to x dot s. Okay, we get dsl x s x dot s, and because we've done this right in this manner, we're translating it to this kind of new function. If we take the differential of it, d over d of ds of l, that should just be equal to let me just separate this so it doesn't become too ugly. Then that should just be equal to 0. Okay, it did become ugly. Oh well. Because these are in terms of s, these are now in terms of s, so differentiating them, and they've only got one variant of s, differentiating them should give differentiating the Lagrangian should give us 0 in this case. We can then also this claim as well to follow up with it. We say c is equal to the momentum dx s over ds. The momentum differential of xs over ds, and if we were to differentiate c, it would be 2 equals 0, and that can actually be proved quite easily by going through, differentiate c with respect to x, differentiate the momentum with respect to x, and differentiate this part with respect to x, so on and so forth. You actually end up with zeros because the terms cancel out, and you realize that a lot of these parts aren't reliant on each other, dependent of each other, and so they just end up equaling 0. And if the differential is equal to 0, it is by definition a conserved quantity, and if it's a conserved quantity, notice symmetry here is maintained, and this kind of proves a symmetry for these coordinates. Now, this is kind of the basic way of proving it, but I think it's a bit kind of wishy-washy towards the last step, so I feel like we can more of a general idea of it, even more of a generic idea that really helps you understand this. Cool. Let me see if I can. Okay. So, is it a bit more of a generic way of thinking about this? I suppose this is another little example. Suppose now that we take the symmetry and we replicate it using, we make symmetry, and the new symmetry goes as follows. And this is a really basic symmetry. We say that x of t goes to x of t. Right, notice that this is completely different from here where x went to a new function variable. X of t goes to x of t plus an infinitesimal change, call it epsilon, right? Now, if that is the case, then what would happen if we differentiated x of t? We would simply get x dash of t. God, that looks terrible. we would get x of t goes to, well, what happens here? We get x dash of t, but this is just an infinitesimal change, which is a constant which disappears when you differentiate it. So x dash of t goes to x dash of t. The variables themselves, t goes back to t. So, in essence, what we have said here is we use this symmetry. We translate x of t by an infinitesimal change epsilon. We just add it onto it. And when we do that, we get, it goes to xt plus epsilon. We take the differential of both of them, we get x dash of t going to x dash of t, which means that t goes to t. That's the symmetry right there. That's the same kind of, that's a very similar symmetry to what I had here, but this is just with additions of infinitesimal changes. But in all essence, the symmetry stands because the old values are getting mapped to the to identical new values, even though we have translated it by some amount. Okay, and that's all it really is. It's that. So let's just go and have a look at a quick exam question. This one I saw in A section of an exam, which nicely just tackles the idea of Noether symmetries. Right, let's just minimize this. Right. So, in this exam paper, in the A section part, as in many exams, you get this in the A section, I to A7 and A8 here. So A8 is the actual question we're looking at. For the system described in A7, what would the Noether symmetry responsible for the conservation of P1 be? So we have to look at A7, of course, since it's describing a system in A7. The system is being described here. Consider Lagrangian L with these two generic coordinates, Q1, Q2, and of course their velocity components, of a conservative mechanical system described by generalized coordinates Q1 and Q2. What condition must the Lagrangian satisfy in order for the momentum associated to Q1 to be conserved? Essentially, for us to prove that the momentum associated to Q1 is conserved, we just have to prove that the Lagrangian is independent on Q1 in this case. Right. Do that. Let me whip out the exam solutions, show you very clearly how to do that. We use the Euler-Lagrange equations themselves, the equations of motion. So we got d over the d dt, dl over dq1 is equal to dl1. Just as I showed you earlier in my example. You know that we can call this p dot, essentially, because this is p. This is defined as momentum. This component here. I hope you can see my mouse on the screen. You can, good. This is p, and this part here is dt. So we're just differentiating the momentum with respect to time. We get p dot 1 is equal to dl over dq1, of course. It's conserved, like I said, it's conserved if dl over dq1 is equal to 0, if the Lagrangian with respect to q1 is equal to 0, and that is only the case if L is completely independent of q1. That's the condition that it has to satisfy. That's the condition that it asks you to state in the question. If you say that L is independent of q1, that's it. Cool. So L is independent of q1. What would the Noether symmetry be? Well, going back to my example, the way of thinking about this one could be done very similarly. Simply notice here, again, like just looking back at the very last part I did, we translated it by some infinitesimal change e, right? And when we differentiated it, it disappeared. And here, if you look at it, the Noether symmetry is kind of satisfied when the differential of it itself kind of not disappears, but it essentially equals what it equaled before. And so you haven't actually, you've translated it, but you haven't made any changes to the values that you're getting out of it. That's a way of saying it, I suppose. So in this case, if P1 is conserved, and then L has to be independent of Q1, well, if it's independent of Q1, think about it this way, we can translate it by any one value, right? We can translate it by any Q1 value, and dl over dq1, because Q1 doesn't depend on L, right? Any translation by that would disappear once you differentiate it. So the answer for A8, right, for the Noether symmetry question, what's the, what was the actual question? what would the Noether symmetry responsible for the conservation of P1 be, right? The Noether symmetry responsible would just be translations in the Q1 direction. And it's as simple as, it's just a few words that you have to put down to get the marks in this question. And I hope I've explained to you why that is. So, enjoy the video, like and subscribe, although only 2 people are going to watch this. Big shout outs to my friends Hamza and Frank. Love all of you. Bye bye.